Okay, everybody. Next topic in physics here this week. We're getting into some applications of energy and work, and that leads us right into simple machines, which I'm sure you've all heard of. Today we'll learn the physics of how those create a mechanical advantage and magnify a force. We need to begin with the idea that energy is conserved. As we stated last week, um, and we know that work is our unit of energy, or at least how we change the energy of a system. And what I have to start off here is an expression showing how work or energy is conserved in a system. So if we think about how a machine is going to give us a mechanical advantage, we need to realize that there's no free lunch. We're not getting something from nothing. What we're doing here is we have a trade-off, and the trade-off involves understanding the definition of work and where that trade-off lies. So if we know that we're going to do some work using a simple machine to make our input force smaller, the trade-off has to do with the distance that the force is applied. If I expand this expression to show that work is force times distance, input is going to be equal to work, which is force times distance output, you can see how if we are going to decrease our input force, we're going to try to make it easier, well, we're going to have to apply that smaller force over a larger distance. We'll get the same work or energy value, but we can do it differently. And a lot of times we can exert a small force over a big distance. We just don't have the strength to exert a large force. So we'll happily take that trade-off. And my output work will have a magnified force, so we're going to usually lift some heavier load, but the trade-off here is that the load is only going to go a small distance. And so the trade-off primarily comes in the distances that the objects move, and the benefit comes in the forces involved. How does this relate to the concept of mechanical advantage? So mechanical advantage tells us by how much we can magnify our force. And so what I like to use is the notation F sub I and F sub O. Sub I means my input force, and sub O means my output force. Your textbook likes to use F sub E and F sub R, but I think it's a little more intuitive to just use in and out. But don't let that throw you off too much. So what we want to do is we want to look at the ratio of these two forces to determine our mechanical advantage. And if you get confused about which force goes on top of the fraction, generally it's going to be the larger force in the numerator and the smaller force in the denominator. If that's the case, we're going to have a bigger number divided by a smaller number, which is going to give us a whole number, and hopefully a large whole number to have a large magnification of your force. There are times, however, when our output force might be smaller than our input force if our goal is not to magnify force, but maybe if our goal is to magnify distance. And we see that in the rear cassette of a bicycle. And moving at high speeds, we actually don't want to make it easier to pedal. We want to make it harder to pedal and have that back wheel cover a bigger distance and allow us to go faster. So a simple example here to start with would be if my output force of some random machine was 15 newtons and my input force was 5 newtons, that mechanical advantage would be 3. And we call this the actual mechanical advantage. And we differentiate that from ideal mechanical advantage because an actual mechanical advantage is going to take into account the friction in a machine. The ideal mechanical advantage does not take into account friction. And we can calculate the ideal mechanical advantage of any of the 6 machines by looking at the output distance divided by the input distance. And that'll give you a number very similar to the actual mechanical advantage, but oftentimes it'll be just a little bit more because there's no friction involved. And if we ever want to look at what the efficiency of the machine is, we'll just look at the ratio of the actual mechanical advantage to the ideal and multiply that by 100%. So oftentimes our actual is going to be slightly less than our ideal because of friction. And depending on the machine, a lot of the simple machines are actually pretty efficient other than maybe the inclined plane. Um, so our efficiency should be pretty high values, like 90% or something like that. If you don't know the mechanical advantages, you can also determine efficiency by looking at the ratio of the work done. So you can look at your output work divided by your input work and divide those two, and it will give you the same efficiency. So let's get into some of these machines and see how these equations are applied. So we'll go through each of them. Your book has some nice images of each of these, which I've basically drawn out for you. Um, and I'll go through the how you calculate the ideal mechanical advantage for each machine. I did not include these on the equation sheet for this unit, but that might be something you'll want to add to them. So here we go. Here's a lever. And if I have a load on the lever over here, some sort of box full of stuff, if I want to lift that load up, I'm going to have to apply a force on this side of the lever down. So typically I don't want to have to apply a big force to lift a heavy load, so I'm going to need to extend the lever arm. And we know about torque already, so what's happening here is we're getting a mechanical advantage, which can be calculated by taking the input lever arm, the side that you're pulling on or stepping on or whatever, divided by the output lever arm, which is the side that the load is on. And whenever we look at the actual mechanical advantage values, for those cases, we'll take the ratio of the forces involved. So when you divide your forces to find the actual value, your bigger force is going to be the output force. And so that's going to go on top. And the smaller force is going to be your input force. That'll go on the bottom. So your mechanical advantage should be a whole number, ideally. The inclined plane, the way we figure that one out is we look at the ratio of the length of the slope here divided by the height that you actually move vertically up. And so let's say I had a length of 10 meters and a height of 1, you would simply divide 10 by 1, and your ideal mechanical advantage here would be 10. Your input force is going to be the force parallel to the ramp, and your output force is just going to be the weight of the object. So that's going to be equal to gravity. With the wedge is basically two inclined planes sandwiched together. Our ideal mechanical advantage is the length of the wedge and the divided by the width of the wedge. And my input force is the force driving the wedge down and in. So if we think about an axe maybe. And the output force is interesting because it moves in two directions. So the output force is split in half. Half of it moves to the right, half of it moves to the left. The pulley system is a commonly confused uh, machine. A lot of people think that if you have one pulley in a system like this, let's say I have my input force here and then I have my load, which would be my output force. That's actually going to be moving up, but the weight would go down. That people think that that's going to give you a mechanical advantage, and so that misconception stems from the fact that it might be easier to pull with a pulley, but mainly because of the fact that you can use your body weight to assist as you pull down. So a lot of times that's easier than lifting up. But actually your input force is going to be equal to your output force. In that case, there's a mechanical advantage of 1, which is no advantage. So to start getting a mechanical advantage with pulleys, we have to have a movable pulley, and the mechanical advantage is just the number of pulleys in the system. So if I want to get a mechanical advantage of 2 here you can see I have 2 pulleys. As I pull, the way I set this up with the block and tackle system, this pulley is going to be moving up towards the maybe stationary pulley. And that will give us a mechanical advantage. And then we can start to see the trade-off in the distances that we're talking about. So we'll pull the rope quite a long ways, but the weight, the output force, whatever that is only going to move half the distance. And getting back to the wedge and the inclined plane, in the lever, we see that trade-off, and the load on the lever doesn't really move that far. The inclined plane, we don't really move up that high. The wedge, we go a lot deeper than we spread, and so on and so forth. And the last two, the wheel and axle, is basically 2 circles. There's going to be a larger circle and a smaller circle. And so what I have drawn here is sort of the picture in your book. It's probably better in the book. But here's my axle. Maybe I have a rope wrapped around the small, like the shaft here. I'm going to have a bigger wheel with a rope that's pulling down. And so I'm moving the big wheel and the small wheel together, and both in the same direction clockwise. But the load as the cord wraps around the axle as it's lifted doesn't move very far when compared to the distance that I have to go for the larger circle. And so when finding the ideal mechanical advantage for wheel and axle, we're doing the radius of the input wheel, so that's going to be the bigger wheel, divided by the radius of the output wheel, or the smaller wheel. And like I've said, for all of these, my input force and my output force ratio is going to be how we find the actual mechanical advantage. For the screw, the IMA is 2 pi r, the circumference of the head of the screw, divided by d, which is the thread gap, the distance between the threads. So if I have a screw with the threads are really close together, like a machine screw, that's going to give me more of a mechanical advantage because that d value is going to get even smaller. So the smaller we get our denominator for all of these calculations finding ideal mechanical advantage, the better off we're going to be to magnify our ideal mechanical advantage. And one last thing about machines, a lot of times we have multiple machines working together in unison. That's called a compound machine. If you want to find the mechanical advantage of a compound machine, you multiply the individual mechanical advantages for each machine in the system. So if we start to add up machines, you can see the mechanical advantage is going to start climbing dramatically. And that's something we see a lot in actual engineering is machines working together in unison. So multiply the individual mechanical advantages together. That's it. That's all I got. We'll do examples and stuff for our bell ringers during the week here because we'll need to do a fair bit of that to apply these concepts to some physics situations. All right, guys. Have a great day.